a little bit about what a virtual switch is. Basically, it's a software module that runs on a server node, and it enables network services for virtual machines or containers, VNFs in general. So basically what that means is you can get east-west, using a virtual switch, you can get east-west traffic, that's traffic between virtual machines, north-south traffic, so traffic from the virtual machine to the physical network and back the other way. And more advanced and sophisticated virtual switches enable other kinds of network services. So for example, they may do tunnel termination on the host. So you may send in VXLAN traffic and the virtual switch would decapsulate it and send the decapsulated traffic up into the virtual machine. Careful of that. It also does things like quality of service. So you can rate limit traffic going into a virtual machine or coming out of a virtual thing and things like that. And generally there's some kind of controller aspect to it. So you're able to control a virtual switch or a group of virtual switches using something like OpenFlow, for example. So OVS is one example of a virtual switch. It's probably the most widely deployed open source virtual switch, and that's what we're going to talk about today. And it's interesting for this crowd because very recently, about a year ago, some DPDK was integrated into Open vSwitch. And it's made me think over the last couple of months, there's a question I've had for myself, and I think this is actually a good audience to ask that question, is I think it's probably the first example of a pretty large open source project that's integrated DPDK. Is that true? Or are there other examples?
There is at least one. There's a competition from transfer networks.
Okay, so there's another example. Either way, I think there's very few that have done this so far. And it's interesting because I don't think OVS users actually know about DPDK or understand how to use it. And I also, probably a lot of the users don't even want to use DPDK. All they really want is really, really fast packet processing performance, and they don't really care how it happens. They'd rather it worked just like OVS. So what I'm going to do first, my section is talking about the architecture of OVS, and I'm going to talk a little bit about how it's evolved from its initial implementation through the years to now to the point where we've integrated DPDK acceleration into the virtual switch. So at the very start, first of all, Open vSwitch is an OpenFlow compliant switch, which means that you can program the switch and program this OpenFlow packet processing pipeline using a controller. And the very initial versions were actually all in kernel space. So the whole thing was done down here in kernel space. And that was great, but there was a lot of disadvantages to working in kernel space that a lot of this community know. So for example, the performance wasn't great. It's very difficult to develop in kernel space. You dereference a pointer, a null pointer, and you have to walk across the building to reset your board. And also it's difficult to upstream changes into the kernel, or you'd have to maintain an out-of-tree driver. So what the community did is they split the architecture between user space and kernel space. And that's good because you still have an OpenFlow compliant switch, so using a controller you can still program your OpenFlow packet processing pipeline through user space, but you only maintain a small portion of the switch in kernel space, which is this microflow cache. The microflow cache is basically an exact match table, so it extracts some fields from the packet, it gets a hash of them, and then it just looks up the table to figure out what to do with the packet. So the flow for packets that arrive in this architecture is that they arrive, they see if there's any, the microflow cache holds basically recently used flows, so they see if there's any entry in the flow table for a recently used flow, and if there's not, it makes what's called an upcall via the netlink layer up into user space, which incurs the penalty of a context switch, and then it will traverse the packet processing pipeline in user space to figure out what to do with the packet. Once it's decided what to do with the packet, it then does that thing with the packet, and then it'll install a flow in this microflow cache so that subsequent packets that come into the cache can get handled by that table. One of the issues with this is the cost for setting up a flow is actually quite expensive because you have to make this context switch from kernel space to user space. And the guys in the community came up with a lot of different ideas of how to improve the performance in this case. So they would do things like batch upcalls together, so you'd amortize the cost of the context switch across a number of upcalls. They also introduced more threads in user space, so you could have more threads handling these upcalls in parallel, and that helped improve the performance of the flow setup time. However, it's still quite expensive. So what they did in version 1.11, which was probably about a year and a half ago, maybe 2 years ago, is they introduced something called a megaflow cache to help improve the performance. So a megaflow cache is actually a wildcard classifier in the kernel data path, instead of the microflow cache, which would have been an exact match classifier. And the advantage of this is with a wildcard classifier, each entry can match on more packets, because a single entry, you can wildcard certain fields, and then many flows will match in that single entry and won't have to traverse this netlink interface up into user space and incur the penalty of the context switch. So that really helped to, well, it's a good way to improve performance. However, as Constantine, I think is somewhere at the back here, knows, implementing wildcard classifiers and ACLs in software is quite expensive. So what they had to do then is they also had this microflow cache as well underneath the megaflow cache to help improve performance. But generally that gave better performance, particularly in the presence of a lot of new flows getting set up. So yeah, in parallel to this, actually one other thing I want to point out is in Open vSwitch, the microflow cache is called the EMC, or the exact match cache. Kevin will talk about it a little bit later. The megaflow cache is implemented, it's called the data path classifier. And then up here you have the OF proto layer, which does the packet processing. So that's kind of relevant for something that Kevin's talking about later on. So in parallel to that, Intel decided that they wanted to show that, you know, packet processing in software, or sorry, in user space using DPDK, you can get really, really good performance, as everyone in this room knows. So what we did is we forked OVS, and we created a POC that basically moved all this stuff into user space and used DPDK to show excellent performance. And that was quite successful. We got some very good, promising results in terms of throughput and latency. And that helped encourage or influence the Open vSwitch community to then accept these changes into the upstream. So now in the upstream, you can get a user space data path. It was always there. There was always a user space data path in OVS. It was just poor performance and not really well maintained. So now you can get this user space data path. They push it all up here. They use DPDK. They use pull mode devices, and you can get really, really good performance. So that was quite a good thing. So if we look into the architecture in a little bit more detail, and we'll see how that is achieved. So this is more a structural representation of the code in OVS. There's kind of three main components. So you have OF Proto, NetDev, and DPIF. So NetDev represents network devices. DPIF represents Open vSwitch data path. And an Open vSwitch data path is basically a wildcard table, an ACL table, with a load of ports associated with it. And then OF Proto, which represents an open flow switch. And then OF Proto will use NetDevs and DPIFs to then represent the data path as an open flow switch, and then your management interface, which could be OpenFlow or OVS DB, which is a management interface, a proprietary one created by the Open vSwitch community, could then control that and configure your switch in many different ways. Each of these components has an interface, a very well-defined internal interface, and you can write your own implementation for this interface if you want, for these interfaces, if you want to port it to your own technology. So for example, you could write an implementation of your OF Proto interface to port it to a piece of hardware, as an example. And also within the code, there are a few implementations already there. So for example, the DPIF interface has two implementations. There's DPIF Netlink, which is the kernel space data path, and DPIF NetDev, which is the user space data path. Similarly, for NetDev, there's a number of different implementations of the NetDev interface. NetDev Linux for Linux interfaces, and NetDev DPDK for DPDK type interfaces. So Open vSwitch with DPDK is basically Open vSwitch using the DPIF NetDev for the DPIF interface, and NetDev DPDK for the NetDev interface. Within NetDev DPDK, it uses libDPDK directly, and it takes advantage of the different types of interfaces that are available in DPDK. So ring interfaces, VHost interfaces, and physical NIC interfaces like the pull mode driver. Currently, that's really the only place we're using DPDK directly, I think we would like to see DPDK used directly, for example, in the DPIF code, maybe using the hash table or the ACL table or something like that directly. But currently we only use it here. However, we do make software optimizations in a similar kind of optimizations the DPDK community make. We do make them also in different portions of the code. And actually, as a bit of a side point, the Intel fork of OVS created a different DPIF, so it was DPIF DPDK. So that was the different architecture between OVS with DPDK and the Intel fork of OVS. So if I delve into a little bit more detail about the different interfaces, I think maybe a lot of people here will be familiar with this, but I'll talk about it anyway. There's three main interfaces, as I mentioned, in OVS with DPDK. There's the Pulmo driver interface, which allows you to read and write to physical NICs. There's a ring interface, which uses shared memory and the RT ring APIs in DPDK to allow OVS to talk to another process, be that a secondary process running in the host or another process, or a process running in a virtual machine. And the advantages of that are it gives very high throughput, low latency, zero copy. The disadvantages are that it, for live migration, it's a little bit difficult because you're mapping memory. And also there's some security issues with it in its current implementation because you're sharing a big bunch of memory between virtual machines and potentially they're different customers, so there could be potentially some issues there. Another interface that's been implemented is VirtIO vHost. And VirtIO, basically what that does is it's a mechanism for communicate. It's a QEMU standard mechanism for communicating into virtual machines based on QEMU. How that works is it presents a device, an emulated device in the QEMU, a VirtIO device, and then within the QEMU virtual machine, you can attach a Linux network driver to that device and use standard Linux tools like IP, and you can use standard network sockets if you want to communicate with it, or you can use the VirtIO Pulmo driver, which works like any Pulmo driver except it's working on this emulated device. And then in the back end of QEMU and the host, vHost then communicates with the virtual switch. We have a user space vHost implementation, obviously, because our switch is in user space. There is a kernel one as well. And there's two flavors of that at the moment. So there's vHost Qs, which was Intel's initial implementation of a user space vHost implementation, and also vHost User, which is the QEMU standard way of doing vHost. So that's really a summary of the architecture. So I'm going to hand it on to Tom here, who's going to talk a little bit about usability of OVS.
So I've been at the pub while Mark was speaking, and now I'm back. So what I want to talk about is the perspective kind of from an OVS user. And when we mean usability, first so I want to discuss what we mean by a user, who actually uses OVS, and translate that into what advantages, disadvantages, frustrations, lack of frustrations there might be with these people as using DPDK is exposed to them. But in addition, I want to talk about the whole idea and the evolution of DPDK, not in and of itself, but DPDK as a component in OVS. Talk about the advantages and disadvantages of DPDK, and I'm going to tell a little user story from the perspective of someone, maybe basically me, who started working with DPDK as a software engineer and someone's just trying to make things work and accelerate our traffic for a particular application. And then finally, we're going to talk about how we can improve DPK a little bit into the future. So, like we've heard earlier, DPDK is probably, there are other alternate data planes besides the Linux data plane and OVS, but DPDK is the main one, and maybe someone else knows of other accelerated data planes. But the main one really, and the most popular one, is DPDK. And there's also the NetDev interface that Mark spoke of. We'll talk about that a little bit too, in a different way, and how that enables to make basically the use of DPDK to a large degree, with some warts, are essentially invisible to the users of OVS. So again, the DPDK is great. We can forward packets blindingly fast, as we all know, especially for small packets, and enables the use of commodity hardware. So we can cut the cost of OPEX or CAPEX. I'm not a business guy, so I always get OPEX and CAPEX confused because I don't have an MBA. But anyway, it cuts the cost, the recurring cost, and it also allows the use of DPDK. Allows the use of the basic open flow switch functions are transparent and should work pretty much the same way in DPDK they do with OVS. And of course, the advantages of DPDK with respect to Linux is it's fast. When deployed properly, it's almost guaranteed to be faster. Even if you configure it unintelligently, it'll still be almost. There's a couple of cases where I've seen it be slower with VHost coups and so on, but generally it's a real advantage. But on the other hand, Linux, the advantage of Linux Dataplane is it's familiar. Its device paradigm is familiar to people. It has rich debugging tools, the ability to dump packets. There's just about any interface in Linux you can forward a packet to. And of course, you have a wider variety of tunnel endpoints available, which really are sort of there but not quite there sometimes in DPDK yet. And most but not least, or least but not most, is the full set of device statistics are available. And that's a little bit abbreviated in DPDK, and a full set of metadata for the devices are carried through and made visible. And on the other hand, the DPDK's main advantage is just fast. It's mainly, and this is again, I'm talking about the advantages from the standpoint of someone using OVS. So who are these users? As I said, they're basically controllers of open flow controllers, open daylight, Ryu, what have you, various other controllers. And also the implementers of the OVS DB protocol, like Oven is a big one, or the OVS DB plugin for Open Daylight that basically manages the provisioning of ports and bridges within OVS, as well as programming the flows. And they all, hopefully, in many cases, can be set up in such a way that the fact that we're using DPDK is invisible, except for that it's faster. Or at least that's our ideal. We don't always achieve it. Another user, of course, is the people using the OVS CLI, like OFCuddle and its companions that you can configure the switch and look at all the things that are happening in the switch if you log into the VM or the physical server that's actually running OVS. And they can pretty much do the same thing with DPDK that they can do with the Linux kernel. Of course, cloud, whoops, there's a misspelling, sorry. They're cloud deployers, programmers, people writing applications on top of it are users in effect. And we would like them to have a fairly simple interface so they don't have to know too much about the gory details of the underlying architecture, enough to optimize. I mean, many programmers are quite familiar these days with thread pinning and how to optimize multi-threaded programs. They understand some concepts of multi-core, but some of the cache coherency issues is difficult for a lot of people just not familiar. And it'd be nice somehow if we don't have to expose all those things to all the people using OVS. Then I'm also going to talk about, break in the middle here to talk about a user's experience. And then finally, we'll talk about what really do users want and their expectations of DPDK OVS. And this is kind of based on gleaning of conversations with postings onto you know, the OVS mailing list and so on. And hopefully we can stimulate some controversial discussion, which will wake us all up. And so in the beginning, the user I'm going to talk about is me. So, because that's one person I know. And I think, sometimes I'm not sure, but in 2013, at the ONS conference, I saw an Intel presentation. I said, wow, this is blindingly fast. And I was working at the time on security applications. And there's all this talk about, you know, the different things we could do with different very, very expensive front ends with very, very expensive silicon and FPGAs to capture packets extremely fast. And maybe we could go at 10 gig and 100 gig. In the security community, they didn't mind so much throwing tens of thousands of extra dollars on a box in order to capture packets for analysis for, like, for example, to train machine learning and things like that. And then I was asked to work on a team developing a product that was a threat analyzer that was trying to find a price point that was way below the competition. Now, they currently had a plan. We had a prototype running on the OVS Linux kernel, and it was great for doing DPI and analysis at 1 gig rates, and we proved that. But we didn't have a path going forward to 10 gig without breaking the price point for sales. Whoops. In spite of all my training on this, I'm still hitting the wrong button. So what the idea was, I said, hey, I think we could use this DPDK, and we don't have to buy an expensive front end. We can just use the standard PMD interfaces, and we can go at optical rates. And they say, well, can you prove it? Well, I don't know. So was DPDK the answer? And so they wanted to build a strategy around this looking forward. So I started out with DPDK 171, and I had already been familiar with OVS. I'd been using that for a year or two, and open flow programming and so on. So that was and then I had integrated OVS Linux kernel into the box, and then things started to get very confusing for someone. We had the 171 integration, which really wasn't quite integrated with OVS. We had the o1.org fork, which Mark might know something about, and which showed you that it could work. Well, we had to integrate this with an application. We had to integrate it with a DPI path, and we also had to be able to remotely manage just the flow of packets for traffic shaping and threat blocking and mitigation and things like that at least in our plan, even if we weren't doing them currently. So, and then the third thing was the DPI fork that was done by Cosmos, and that had a custom interface, and Frank and I were just chatting about that a little while ago. That had a custom interface for the Cosmos' DPI engine, but it didn't really give us a good way of going forward and managing the flows ourselves. And also it wasn't quite integrated yet with, it didn't seem to be, it was a fork, it didn't look like it was going to be accepted as an addition to OpenFlow, and it would have been better to just work with interfaces. So what happened with 1.8 came along, and then everything just kind of fell together. With 1.8, we were able to, using the master branch at least, without the release code for OVS, was able to get DPDK working. I was able to demonstrate performance improvements without hardware because they wouldn't give me any hardware. So I was able I used, I'm sorry to say, I hope there aren't any Red Hatters listening in here. I used VMXNet 3 because that's what I had, and it worked well as a pull mode driver. So I put DPDK in a VM, and I was able to swap out VMs, one with the Linux kernel, one with DPDK, and use some packet generators, and showed a 2.5 performance advantage. And so this was without a lot of tuning. It was just using 2 cores. And I said, doing simple forwarding. So it really looked promising, you know, and they said, okay, good, this will be your future. And it looked very, very, very good. So the next thing I did is I wrote a simple, some simple code basically to replace the PCAP layer in the DPI engine with DPDK ring, and got that more or less working. It wasn't great. It wasn't tuned properly. The thread pinning and usage in the DPI engine wasn't quite aligned with what was going on in the DPDK, but we saw that we could do it, and main thing is we had a device that we could forward packets to if we wanted them to be analyzed by DPI by using the DPDKR interface in Open vSwitch. In other words, since it was done in DPDK, and DPDK had, as Mark pointed out, an interface type, DPDKR, that was basically a device that we could manage through OVS and forward traffic through. So it worked out quite well. Now we're up to 2.1 and pretty darn close to 2.2. So a lot has happened in the last, and this was work that I did, and others did toward the end of 2014, the beginning of 2015 actually, so it really wasn't that long ago. So a lot of it, and I'm going to kind of blast through this because I think Mark probably covered it better than I am. But the really thing that makes it transparent, and Mark talked about the DPIF, but also it's the NetDev that really makes a device. So OVS doesn't really know, in a lot of ways, whether, or care, whether the device is implemented by one data plane or another. And this allows what I call the transparency, the data planes. It allows, the NetDev interface allows the Linux data plane to behave very much like the DPDK data plane, or, heaven forbid, in this community, the Windows data plane, which I think is the third one that's received a lot of attention. But that really has helped to expose for OVS developers a really generic and very robust data plane to user space. Well, they call it user space, but what they really mean is that OF proto part of OVS. So the NetDev is very similar to the network driver interface in BSD, as anybody who wrote drivers, and it's a little bit like Linux kernel in the sense that it abstracts the details of the device. It has a start, a stop function, it has queue management, and then tacked on the end is a private area that the devices can use. So it's similar in concept to DPDK. And what that makes so is that the architecture gives you the transparency and gives you a nice layered approach. I want to say that coming from a networking standpoint, and I'm sort of a developer, but I'm kind of a networking guy too, and I like network engineers a lot. I think they're really nice people. And so the network engineers want to see things look like something they can manage from the high level, right? And it's the same thing with orchestrators. It's the same thing with people using Neutron, standing up clouds. They don't want some kind of device that requires little special funny parameters that they have to do extra things in the orchestration, and particularly when it's not in their skill set to understand what those are. So I'm getting ahead of myself a little bit. So let's go on to how we can improve Open vSwitch. Now, if you look in OVS and look at the install.dpdk.md, a lot of us have wanted to see this experimental go away. And I think there was an earlier attempt to submit this patch, and it didn't go anywhere. It's probably time to try again. So this led to some discussion, which was interesting, about ways that DPDK could be improved in order to get accepted as being non-experimental and sort of a first-class citizen within the OVS community. And kind of irks some people that I don't think it says experimental in the Windows data path, but that's interesting. Anyway, so how do we improve this? So let's talk about some of the suggestions of the thread. One of the issues, and I believe I may have glossed over this earlier, but one of the issues with DPDK is the device management, is the fact that we have to use this nickbind utility to disconnect the device from the Linux driver and reconnect it as a poll mode driver. And it seems a little counterintuitive to people, you know, deploying OVS. There's other aspects of device teardown, device bring up. People say, well, Linux does this, great. The Linux kernel does this, why can't you do it? But it's really not done in the Linux kernel. The network device management isn't done in the Linux kernel. It's done by, these days, in modern Linux, by udev systemd, brings up the devices, brings them down, and manages them. Why can't we manage, well, or maybe we should be managing NetDev, DPDK NetDev devices also with udev systemd. So this suggestion actually was made by Flavio Leitner, so I got to give him credit. It's just like, seems like a really sensible approach. And then there's other ideas as well. Another way to improve is people complain, and this is true, there's no way to dump packets. There's no way to say TCP dump -I and they give it the DPDK PMD device driver name. Now I realize dumping packets from a 10 gigabit or 40 gigabit device is probably unrealistic, but it'd be nice to have some kind of visibility in there, and like historically, like some of us, and actually Kevin's going to talk a lot more about debugging in a few minutes. But so maybe that's one thing maybe we could do, but we know how to do it, right? But we don't have the command that's available to the user just to say like DPDK dump -I and then an interface. But that, we could do that in OVS by mirroring the packets to the PMD libpcap, maybe, and then you could capture packets there, or libpcap-ng. And that's something to think about for those of us that are interested in submitting patches for this. Whoops. So for testing, one thing is that was discussed was to add, Tomas' presentation, he talked about CI testing and some efforts of introducing CI testing, but to do Dataplane testing of different devices would increase the confidence that people have of DPDK. There's nothing wrong with it. It's just it's a pretty broad what do you call test target to deal with. Another is projects like VSPerf, and another thing that kind of, this is just like a net that some people come in, is the supporting of two different types of vHost devices, vHost COOs and vHost user, and people try to make vHost COOs go away, but we can't seem to make it go away, even though it doesn't work very well. And the vHost user is really more universal, and it's easier to configure and doesn't require this funny socket. And from a person trying to provision a device, I don't know how you would use vHost COOs if you're trying to provision it via OVSDB or something like that. But you can do it with vHost user. Pretty much looks like any other device. Better documentation. Now I think Kevin just submitted a patch to install the dpdk.md, which really clarifies things quite a bit, and there's been other efforts as well. And another thing is training, or a tool that would somehow, that might do an LS topo type picture of your architecture in your server or wherever you're running, and automatically, instead of going, oh, see, I got this Newman node and this core here and that core there, and just somehow compiling all that information and then generating EAL options or whatever out of that, EAL options and socket mem options for DPDK to help make that invisible. It might not catch every case, but might give users, as I call them, a better shot at trying to optimally use DPDK in their open vSwitch instance. And I think I'm about ready to turn it over to Kevin. And if you have any questions for me, or you go ahead. Otherwise, we'll answer questions in the end, and Kevin can proceed.
Okay, thanks, Tom. Okay, so I guess Thomas talked about usability, Mark talked about architecture, so we'll talk a little bit about performance now. So I guess, what kind of things can we do to make sure we get, better and best performance in OVS with DPDK? So we're going to hit just a little bit of basic system tuning, some scaling out that we can do in OVS with DPDK, and then we'll talk a little bit about some of the code optimizations that are ongoing. Okay, so just to give an example, packet flow, we have a case here in the red where we have packets coming in through a physical port, being switched in OVS, going through a virtual port, maybe vHost user, up to the VM, there's some packet processing happens there, and they come back down, switched again in OVS, and sent out to the physical port. So by default, in this case, we're going to have a lot of stuff running on Core 0. So, by default, the operating system will schedule some stuff there. Our VM processing, so our vCPUs mightn't be pinned, they might run some stuff on Core 0. Hopefully we wouldn't get the actual packet processing and forwarding, but we probably would on Core 0. And then on OVS, so we're going to be doing a couple of things here. We're going to be trying to pull packets from the physical port, figure out where they need to go, and then send them on their way. And similarly on the from virtual port 1, we're going to get packets, look them up, see where they need to go. So there's a lot of packet processing going on. We want this to go as fast as possible, and we're really going to suffer because Core 0 is going to be completely overloaded. So, luckily for us, there's things we can do. So if we start with basic system tuning, so we can isolate use the isol CPUs on the kernel command line. So we can say, the operating system, you can use that Core 0. We'll use the other cores for switching and VMs. So we can core affinitize, I guess, our vCPU in QEMU. So we can pin that on a particular core. So we pick Core 9. So keep that out of the equation for switching. So what we've done here is we've put 4 cores for OVS, and we've made each one of them responsible for an individual port. So rather than the case of where, in the previous slide where we had 1 core and it was trying to service 4 ports, we now have a core per port. So that way, if we're trying to read packets from physical port 0, virtual port 0 is not, there's no packets building up there, we're not waiting to service it. Okay, and in this kind of scenario, like 4 cores would be ideal. But of course, we might want to give 4 cores for forwarding in the switch. So, obviously you could scale it down and put 2 cores or put 1 core. And that kind of thing can be dynamically changed even as packets are in flight. So it's very programmable. Okay, so the next thing is, so I've picked core 1, 11, and 2 and 12. Could anybody hazard a guess why I picked those core numbers? Yeah, okay. Yeah, well, I didn't really tell you what the system would look like, so it was a bit of a trick question, but you're right, that's what I was thinking, hyperthreading. So I was thinking that this was a single socket, 10 core part, but we enabled hyperthreading. So hyperthreading, is running 2 logical cores on 1 physical core. And for an application like OVS, where it kind of scales well with cores, it's really, free performance, or free performance boost, I guess. So I picked, so 1 and 11 are thread siblings. So these logical cores, core 1 and core 11, both run on the same physical core. And similarly with 2 and 12. And we'll see later on the performance boost from hyperthreading, but it gives us a good boost. Okay, so at this stage we could look at OVS and say, well, in this scenario we have a core per port. We can't really get any better than that. If we had a 5th core, what's it going to do? But we can actually scale better through queues. Okay, so multiple queues makes for better scaling out of performance and much more cluttered and difficult to explain diagrams. But we'll take that trade-off. Okay, so we've had the concept of, say, cores pulling packets from ports and then looking them up and forwarding them on their way. But what about if we could split the traffic from that port into multiple queues and then assign cores to those queues? And that's what we can do. And again, it's a simple command line on the OVS, using OVS app control to do that. So in the physical case, that's already there. The code is upstreamed and it's using receive side scaling from the NIC. On the virtual case, so what I'm showing here is not fully upstreamed yet. So at the moment, even if we did scale it on the physical ports, we come in and we have a choke point on vHost user going up to the guest. And that's because we have single queue for vHost user. But there's been great work done by the DPDK community, the OVS community, and the QEMU community to enable multi-queue into vHost. And I mean, you would have seen there's patches on them, well, all 3 mailing lists. And I think it just needs a bit of maybe coordination between projects, maybe some testing, and hopefully we'll get there in the next release or 2 of DPDK and QEMU. Okay. So in terms of so that's the kind of system level tuning and scaling out. But what about actually making the code itself faster? So if we didn't want to give OVS that many cores and we just wanted to make things faster on a single core. So in order to understand the optimizations, I guess it's important to understand, well, what things are we actually doing in that packet flow? So what can we optimize? So I guess we'd receive packets from a virtual or physical NIC. Then Mark talked about the different tables. So we would look up in a series of tables, depending on what entries were in there, and try and find a match for that packet. And then any actions we'd need to execute, we'll do, and then we'll transmit it on a virtual or a physical NIC. So ideally, we want to hit in the exact match cache. And this is going to give us our fastest performance. If we don't, we're going to pay a performance penalty in throughput. If we go up to the wildcard classifier, the datapad classifier. And again, I guess the OF proto tables, typically they'd be just the first packets in the flow should hit those tables. So we definitely don't want to go anywhere near this. We ideally want to keep stuff in here, but maybe some things will go into this depending on if stuff gets evicted out of the exact match cache. Okay, so we've an RX cost, we've a cost of lookup, which is variable depending on what table we hit. We've an action cost, and we've a TX cost. Okay. So some of the efforts that I guess are ongoing in the DPDK and OVS communities, some of them have been done, some of them are in progress to make things faster. So for the physical I/O, so we offload the hash that we use in the lookup to the NIC. Okay, so that we don't need to recalculate that hash in software. Multiple queues, I guess that's more of a scaling out thing. That's done for the physical port. So the use of the vectorization functions in the PMDs. So this to me is an interesting one. Tom talked about the usability and being able to use APIs. So I like this one because it gave us a performance boost when we got the settings right to make sure that we had vectorization turned on, and it maybe bumped us 1 million or 2 million packets per second. And that's great, but the other thing is we got really good feedback on the OVS mailing list because it made the code an awful lot simpler. So I mean, the patch for that was to remove this list of custom configs and replace it in the port, the TX and RX port configs with null. Okay, so let the PMD decide what the default should be. If we want to change them, we can do that, but why should OBS try and pick the defaults? Let the PMD do it. And I know for there's many people here, they dream of RX-free thresholds and what the ideal values are, but from an OVS perspective, you know, people don't really care. Bruce is laughing, I think. They don't really care, and you know, this can look like a lot of magic numbers. So I think it's a really good example where a simple change that I think came in and maybe around DPDK 1.8 made OVS, I suppose I'm saying usable, but I'm talking about from a developer of an application using DPDK. Okay, so the exact match cache. So I mean, the first thing we did was, well, you know, we want to try and get as many flow hits in here as possible, so just make it bigger. Okay, that's going to help. So why not make it 1 million entries? Well, you know, then you run into other issues with, you know, your cache sizes and stuff. We looked at integrating one of the DPDK hash tables, but there's a kind of a different usage model at the moment, and actually the hash table in OVS is actually quite efficient as well. So it can have variable key sizes, so slightly kind of different usage models, but that might be something we look at it again in the future. So there's also, you know, before we get to the EMC, there's extracting the kind of flow from the packets and the metadata, and that's something that we're working on to try and optimize because there's a bit of a bottleneck there. So the data path classifier, so, you know, we've looked at the use, and we are looking at the use of the DPDK ACL tables. They give much faster reads than the one that's currently in OVS. But I guess again, it's kind of there's a lot of rebuilds in OVS, so we need to figure out how we can manage that and how we can integrate them, but that's work in progress. On the virtual side, there's been a lot of work, so you know, we've concentrated on the VHost library and in particular VHost user. So I guess when you're going up to the guest through VHost user, you have the VHost library, which is the kind of host part, and the VirtIO PMD, which is the guest part. So, you know, typical kind of DPDK type optimizations in VHost library, you know, the likes of prefetching, bulk allocation. And also then in OVS, so, okay, that's fine, that's in the library, but from an OVS perspective, you know, do we need to lock and update our stats every time we call it, or can we do something different? So kind of the code in OVS, you know, surrounding like the likes of the VHost InQ and VHost DQ functions. The VirtIO PMD, Factorisation, I'm looking for Huawei Z. So he's been doing some great work. I'm trying to see what he could do with Factorisation in the VirtIO PMD. So this is the kind of the guest side of that path up to the guest. And he's also put some, you know, some optimization ideas really for the VirtIO protocol up on the mailing list, you know, so check that out if that's of interest. And again, multi-queue vHost is something that, you know, hopefully will land pretty soon. And I guess, yeah, you could argue that's kind of more of a scaling out thing.
How do you set up the RSS for such configuration? Which hash is made by the RSS?
So it's just a 5-tuple hash, and it would be used in the lookup. So it's...
This is the 5-tuple? Yes.
Yeah. Yeah, so the 5-tuple would, okay, so that's a good point. So the 5-tuple hash would be used to index the hash table.
Okay.
But then when you do index the hash table, you would compare, you would have a greater detail, we would compare the flows. So you would compare other things like port numbers and stuff there.
Okay. Another question, how do you handle the congestion, for example, on the rings and between the blocks? For example, when you have the text path to the virtual NIC, so it's possible the congestion here was...
Yes, so that's...
How are you handling what is that?
Okay, so at the moment, so that gets back to the multi-queue vHost. So at the moment, it's done by locking, okay, because it's only a single queue into the guest. So that has to be done by locking. But you know, the patches are out for multi-queue, and I'd hope that would, you know, give a kind of a parallel path so we can avoid locking. Okay, so some results. Okay, so this is all upstream code. It doesn't count anything that's kind of in progress at the moment. Okay, so we have two scenarios here. It's a bit hard to read. I'll call it out. Okay, so we've one that's just, you know, physical into OBS and back out again. So it doesn't necessarily seem like a particularly useful use case. But really what we're doing is we're putting really fast I/O on it. We're sending packets in, and we're really kind of exercising the cost of the lookups, the flow extractions, and actions. So with standard OVS, I'll call it out in case anyone can see at the back. It's about 1.3 million packets per second, and you can see there's a significant advantage with OVS with DPDK hitting 16.5, and that's just one core forwarding in OVS. So the orange block at the top, which I didn't give a legend so you wouldn't know, is 19.6 million packets per second, and that's the additional bump that we get from using hyperthreading. So again, that would be still using one physical core for the packets forwarding in OVS with DPDK, but we'd be using 2 logical cores. Okay, so the other case then, so PHY to VM, so kind of like the case we looked at in the earlier example, where we push packets into the physical port, up to the guest and back out again. So standard OVS, 0.8. OVS with DPDK, 1 physical core, 4.8 million packets per second. And I'd hope that would increase with some of the optimization that's ongoing. And we can see then this was actually a bi-directional test, and we can see that it scales really well with a second core. So a second physical core, and it jumps up, pretty much, as you'd expect. And again, the orange blocks are, what happens when we get a hyperthreading. Okay. That's it on performance. So Tom is going to talk.
You told me I have to wake up. So in conclusion, we really look at it. Let's talk about or think about the trade-offs between traditional networking with a Linux kernel with Open vSwitch and networking with DPDK, and see that there's a trade-off. And that's what we're going to illustrate here. This is a balance, not a catapult. So we look at, L3 forwarding performance is vastly improved. And then we have the ease of debugging. On the other side, in this example, we're looking at GDB. And the goal is to get something that it just works, something that's intuitively straightforward for users. And we add the orchestration from the cloud. I'm sorry, we add the different use cases. And we add the stability of gaining port statistics. And we tend to have a more, perhaps a balanced picture. And it's just an idea of illustrating that there's a trade-off between functionality and performance, and hopefully, as we move forward, we'll come to the optimum here. And that is pretty much it. We have some other interesting tidbits, and if you have any questions, ask.
So what about the TCP performance?
Well,
have you measured the TCP performance? Because this is a mixed traffic with huge packets and small packets, so it might be different gain, or maybe not a gain at all.
There might not be a gain at all, that's right. And TCP, the way, and from my previous life, I know, and then I think many of us know, but perhaps this is a little bit of a controversial statement. The thing about TCP is once you have a stream established on a fast networking interface, the Linux kernel really optimizes that TCP path. And that where we've looked at, and we're getting the pressure for the highest gains is on UDP and small packet sizes. Yes, Stephen.
You have you will see a fundamental problem right now, which is that the vHost and the VirtIO both don't implement the features in VirtIO to do checksum offload.
Oh, yeah.
And that will cause an actual performance drop in some workloads. I can do some tests between our DPDK-based and our non-DPDK based product, and I'll see some cases where the older product has better performance, and that is strictly due to the lack of TCP offload and segmentation offload.
Yeah, that makes sense, and that's probably a better answer. Right, so you're in comparing the Linux kernel data plane with the DPDK data plane, because the Linux kernel supports
It's really down in the, not
offloads.
in the data plane. You really, the plane goes down to the device driver and the feature bits that get negotiated.
Right, and what users see is we don't optimize those capabilities of those devices, so people blame it on the data plane.
Well, one thing we want to do is we want to try and get some of that offloaded to the NIC.
Yeah.
The NIC can do
But
it.
you really want feature parity.
Yeah, absolutely.
You want, if VHost QEMU latest version supports these feature bits, then we need to have that in DPDK.
And another good example too, that is VLAN handling. VLAN pushing and popping is accelerated in just about every NIC out there in real life. And as we working in Q in the Linux kernel OVS data path, and so that's something we need to take a look at as well. That's a very good point. Yes.
With the IB security control, there was a logic to find the 2 0 between the gas and the gas. What is the option?
Wait for the mic, and we'll hear. Could you repeat the question, please?
With the initial IB/MEM model, there was a logic to have a complete zero copies between the host and the guest. So what would be the approach with OVS DPDK?
Yeah, why don't you? Oh, you don't need this, that's right. He needs it.
So initially, the first kind of implementation of OVS DPDK with IB shared memory was like that. You just share it, and you don't really worry about it. We did do some work in the DPDK project maybe a year ago or a year and a bit ago, where rather than share entire memory regions, like an entire page up to the guest, we would share just individual objects. So you could share a ring or a MBUF pool or something like that to kind of do a little bit more isolation. You can kind of see that maybe the next step to that would be to allow some kind of security zones. So some virtual machines that want to talk between each other, zero copy, could do so, whereas other ones who don't, you'd maybe have to introduce a copy to get better security. But at the moment, that we really only have basic support in OVS with DPDK, so it's just sharing a page up to the virtual machine, and that's mainly because I think VHost has proved to be quite a successful model, and we're getting a lot more traction with users and customers to use that. However, there's still an option to use IB shared memory, I guess, if people want to take up the work and trying to get that working better. Does that answer your question, Vincent? Yeah.
Here we go.
How do you measure the number of the setup connections or the rules per second in your configuration comparing to kernel?
As in the flow setup time?
Yes.
We haven't done it a lot. There are some papers out there. You can see that VMware have deployed Open vSwitch in their data centers, and they kind of show how many, in typical use cases, how many flow setups they get per second, before they introduce megaflows and after they introduce megaflows. However, the number should be the same for DPDK as compared to without DPDK. But the time taken, and that could be the other thing you're talking about, to actually do that upcall is obviously less because you don't have a context switch from kernel space to user space, so there is an advantage there.
What is the number of millions or thousands?
I don't know the numbers off the top of my head. So there is a project in OPNFV, the VSPerf project. I don't think there's anyone from that project here, but the intention of that is to characterize a lot of these metrics for different switches, and that's actually one of them, the amount of time it takes to establish a flow in a switch.
And that's a good point. I'll get to your question, Vincent, but like Mark said, there's also another project in OPNFV called OVS for OPNFV, and where we're going to deploy alternately either an OVS with a DPDK accelerated data plane to be used by the virtual functions, or one without. And then the vSpurf will be able to measure the difference at that point. It's one of many things that we hope to help accomplish.
And with all these optimization which are done in OVS, and all that run on the other CPUs like ARM CPUs, MIM CPUs, and others. Because I know there are some OVS ODP, for instance, or OVS ODP. I don't want to open that topic about ODP, but I'd like to understand the core of OVS, all the optimization which are done. What are the positive or negative impacts it can have on all the CPUs?
So I work for Intel, so I've never actually done that. I'd be interested if someone else has maybe run it on ARM. It's probably a similar discussion to DPDK running it on ARM or Intel, but I don't know. Have you guys Red Hat?
I can answer shortly that basically all the optimizations that are mentioned here are basically applied to other platforms like ARM because the construction of the CPU is pretty much the same. The gigahertz may be smaller, the CPU frequency may be smaller, but they've got the same cache hierarchy and basically all the optimizations apply.
Yeah, and just one thing I want to point out is also some of the optimizations like say Huawei has suggested are protocol optimization, so they would be really chip agnostic.